happen to be in AP Calculus today, and today's date is Thursday, February 6th, 2/6, 2020. That's not 6. Yes, Gio, question.
Do you have self-check and regular calculus?
I'm for this unit, maybe not. I'm gonna try to make one this next prep period because I haven't made it yet. But the answer is yes, and just probably one or two of them. Yeah. Objective. Use a left. Oh, sorry. Who's reading this? Yeah, Arrow. You haven't read one in a while.
Use a left, right, and midpoint Riemann sum to approximate area from the table. Did I have to teach this at some point?
You probably did once upon a time.
Because
Because this is about the time that we did Ski PE last year.
Yep.
Last year we had Ski PE yesterday on the so it was this last Wednesday, I think. Yeah. Anyway, we're roughly at that time, and this is pronounced Riemann. Riemann, not Ray or Rei or Riemann.
Riemann.
Everyone say it with me like we do in kindergarten. Riemann.
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 It's a Riemann sum because it is a finite sum. I can't remember Riemann's first name. He's a mathematician. We name things after mathematicians. So normally the things that we've been dealing with are infinite data. That means I have an infinite number of points. That infinite number of points can make a line, it can make a curve, it can make whatever shape you want. It can have like a sine wave or whatever, right? But this is an infinite amount of data, which means if I'm calculating some sort of integral, let's write it down, like if I want to find the integral of, I don't know, between A and B, I'm just randomly choosing these numbers. Let's say like A is right here, and let's say B is right here. I have to find the area of an infinite number of rectangles, and then I can get an a finite amount of area from an infinite amount of rectangles, which is that weird contradiction that we're always playing with in AP Calculus. But in your notes, just put a bunch of rectangles to let yourself know there are an infinite number of rectangles under there. That's changing today. And again, as I said before, normally I start by not showing you an infinite number of rectangles, but and showing you this one first, where I have a finite number of rectangles. And how you do these finite number of rectangles is important. It affects the types of errors that you'll get. You'll get more or less error, you'll get an over approximation or an under approximation, depending on how you play with this data. So regardless of what happens, I will always give you data. I'll give it to you normally in a table. Like I would say like 98% of the time, it's gonna be given to you in a table. And this is what it looks like graphically. I always like looking at things visually, graphically, before I look at the table, because the table, I don't know, like I don't see what's happening in this table. I just see like kind of a list of numbers. But here I can see, oh yeah, there's like this gradual curve that's happening here. So what's happening? I'm going to do a left Riemann sum, and what that means is I'm using the leftmost point. I think it's, oh man, I might have to be correct and say, yeah, so it's a left Riemann sum. If I'm using a point that's to the left and I come straight out to the right, I'm not going to crash into this point exactly. It's going to be a little bit under that point, and I'm going to make a rectangle. Straight out from this point, out to the right, make a rectangle. Straight out to the right, make a rectangle. Straight out to the right, make a rectangle. And the important thing that I'm doing here is these heights right here, these are not diagonal in any way. They're constant functions. They're nice and horizontal. I know that I'm not the best artist here, or maybe I should say I'm not the most accurate at drawing. Maybe I should get Loretta in here. She could probably draw straighter lines for us. Okay, she cannot draw straight lines. Mr. Brown is also really good at straight lines.
Mr. Brown is, yeah.
And making perfect circles free-handed. But those are our infinite number of rectangles. That's what they look like. And of course, it looks weird to have some blank space there, so I'm going to make some lines here. But it's not an infinite number of rectangles, it's a finite number of rectangles. So this is still a representation of the integral, but not perfect, right? So I still want to say, yes, we have an integral from, let's say that our A happened there and our B happened there. The integral from A to B, there it is. It's that representation. And what is our function here? Our function is capital G right here. So I'll say the integral of capital G of t dt. And I'll say that's my t-axis, sure. And I'll say that's my t-axis here. That's g of t. So this is the integral of capital G of t dt. However, because we don't have an infinite number of rectangles now, this is not equal to the integral. This is approximately equal to the integral. That's the only difference. I only have an approximation now. And again, if you don't know how to say this thing, I say approximately equal to, or you can say approx. Approximately equal to. All right. So The number of rectangles also affects your accuracy. Obviously, if I just did one giant rectangle, only using one point of data and made one giant rectangle, that is a horrible straight line. My data has a giant amount of error. If I have like 2,000 rectangles, that's getting really, well, not close to infinity because you can't really get close to infinity, but it is a higher number and therefore I will have less error. So the more rectangles that you have, the less error you have. Therefore, if I have an infinite number of rectangles, I will have 1 divided by infinity error, which is, yeah, it's basically 0. Yeah, no errors essentially. And that's the cool thing about calculus, right? So let's actually start using these things. I want to show you guys how I'm going to use a left Riemann sum with 3 intervals. That means 3 rectangles. When I say 3 intervals, right here, you can underline this and say this is really 3 subintervals. That's really 3 rectangles. That's what I really mean, indicated by the table below. To approximate the integral between 0 and 7. I'm using that word approximate again. So from 0 to 7, that means I'm using all the data. Sometimes they give you an integral where you don't have to use all the data, so check your bounds. It is from 0 to 7. I am using 0 to 7, all of the data. The shape that you're going to make for a left Riemann sum looks like this. It's a Tetris piece with a tail on the left-hand side. You can probably guess what the Tetris piece for a right Riemann sum is going to look like. It's going to have a tail on the right instead of the left. But I'm going to call this thing the tail in air quotes because that's not really a tail. It's just the data that I'm selecting in the table.
So it's evolved into a Tetris piece now? Pretty sure it wasn't always.
It used to be like a gun with the hand on the left-hand side, and then it wasn't school appropriate, and then we changed it to something else and something. I like the Tetris piece this year. I'm going with Tetris piece. And then your Tetris pieces can look very, very different, like especially when we get to, what do we do, trapezoid rule. Trapezoid rule is a different shape of Tetris piece. But generally speaking, we have this shape, and I'm using that one piece. So I'm saying for this one piece, this one sub-interval that I'm talking about, this one sub-interval goes from 0 to 1. So mark 0 to 1. And then what is the height of that interval? Well, the height goes up to exactly 6. So I'm going to have a rectangle that has a height of 6 between 0 and 1. There's my first rectangle. And then you're going to do that same Tetris piece just shifted over to the right. So now that Tetris piece, the 1 and the 3 are included, and then the tail is covering the 8. So I have a Tetris piece that goes between 1 and 3, mark 1 and 3, 1 and 3, and it goes all the way up to 8.
I like this. This is cool. This I keep even talking.
And then another Tetris piece with a tail that's covering the 12 between 3 and 7. So between 3 and 7, I have a height of 12. This is a case, an instance, and there are going to be about 50% of your instances will be like this, where these rectangles do not have the same width. This had a width of 1, then 2, and then 4. So they had different widths, and that's okay, because it's just finite. If it's infinite, we have to be a little bit more formal about our widths. They're going to be all uniform and consistent. But there they are. So let's go ahead and calculate these areas. So this is 1 times 6. You guys are going to shout these out. That's 6. What about this next area? It's going to be
12. No. 16.
16. What about the next one? It's going to be
4 times 12 is
28. And I really appreciate like you guys being able to do that in your heads, but can you do it if I only gave you the table now? Can you relate what you did on the graph to just the table?
That's 48.
Wouldn't it be the second number minus the first
Wait,
number?
that's not
times
28,
the lower-
dude.
It's 48. Mark the teacher mistake.
Yes, sorry about that. Thank you. Can you relate what's happening graphically to what's happening tabularly? The table, yes.
Second number minus the first number times the bottom.
There it is. Everyone see it? 7 minus 3 times the height of 12. 3 minus 1 times the height of 8. 16. 1 minus 0. 1 times 6. 6. That's your pattern. Over and over again. That'll happen for a left and a right Riemann sum. And it will be very, very similar for a midpoint sum. It will not be the same for a, what's that guy called? A trapezoidal sum.
Do you have to do the interval of this too?
Yeah, what's
So,
the second table for?
I want. You'll see. So, what could be happening here? We don't know. What is the actual function that I'm giving you this table for? Maybe this was from a function that looked like this. So go ahead and sketch this. I'm going to sketch two different functions. What if the sketch looked like this, where it was, I don't know, I'm supposed to have something that looks like an upside down parabola, or a parabola that is like
Do we draw
negative. Yeah, so go ahead and draw that parabola. So let's assume that my function looked like that. So if that was my true function and that was only approximating the area under the curve, would you say that's an over, is our number, if I add up all these together, by the way, we should kind of do that. What is 6 plus 16 plus 48? We actually have to answer the question. I also, wait, are you sure?
No.
That's not what I got. This is, well,
What?
I got 70.
I got
Because
oh my God.
16 plus 6.
22.
It's
Oh,
72.
22, that's what I did.
72.
So yeah, it's
No.
70.
Just-
No.
It's 70.
Because 2 and the 8 will make a 0.
Yeah, 70.
So 70.
Sorry, I just did some weird.
This is how you show your work.
70, guys.
You can either, if it gives you a graph, you can obviously graph it. But this is the quickest way to show your work. You say 1 minus 0 times 6. 1 minus 0 times the height or the tail of 6. Plus 3 minus 8. Or 3 minus 1 times 8. 3 minus 1 times 8. Plus 7 minus 3 plus, or 7 minus 3, I cannot talk today, times the height of 12. This is how we show the work, and then you can simplify it down here in the next step. You can say 1 minus 0 is 1, 1 times 6, and then 3 minus 1, that's 2 times 8, and then 7 minus 3 is 4 times 12. And then even further, we can say, yeah, 1 times 6 is 6, 2 times 8 was 16. These are matching the areas that happened up here. 4 times 12 is 48, and then I add these all together, and I say, yes, they all together add up to, I should do my plus signs
We
in
have to
between.
write all of this?
Yeah, there's a good way to do this.
Or can we just do the like top one?
You can just do this one and then say equal to blank, but don't make a mistake. If you make a mistake, you'll lose your points, right? So if you do it step by step, it's hard to make a mistake. I don't know why this computer does this. Is equal to 70. What are our units? Do we even check up here?
It's hours
It's feet per hour, and that one's in hours. So what should our units be?
Feet per hour.
square.
No, just feet per hour. Right?
Feet per hour? Okay, well, I'm taking the integral of just L. I'm ignoring T right now. If I take the integral of L, what was L in units of?
Feet per hour.
If I take the integral of something that was feet per hour, if I take the integral of a rate,
Oh, it's just feet.
what should I have?
Where's it hours?
Ooh.
Oh, it's feet.
Feet.
It's feet. I took the integral of L, so L by itself was feet per hour. If I ever take the integral, I'm always getting rid of a time unit. So if I had feet per second, and I took the integral, I'd have feet per second. And of course, it doesn't make sense to do the integral of something that's not a rate, because that's just numbers and no context is being added. Okay, now we can, I should have drawn the curve now. So from here, if my concavity is concave down, actually it doesn't even matter in this case. It only matters if I'm going up or if I'm going down. Is this a positive or a negative function? But let me show you why. First of all, is our answer of 70 feet, is that an over or an under approximation for that actual blue curve?
Under.
It's an under approximation. So under here, we're going to say this is an under approximation. 70 feet is an under approximation. There's a few different ways to analyze this, and I'm going to show you all of them. You get to kind of pick and choose. You have to be comfortable with a graphical representation and a analysis representation, I suppose, just from without a graph. Well, if these squares are all underneath this blue line, and there's this empty area happening above each of them that I'm not including, that means I'm under approximating, because I forgot to add up that chunk of area, this chunk of area, this chunk of area. That's why it's an under approximation. But how do you figure that out if I just saw the table? So let me show you what's happening over here. I'm going to give you a brand new function, no table for it, so I'm just, I don't know, randomly sketch. I'm going to choose some random points. Let's choose 120, 020, 118, I don't know, 312. Kind of flipping these all on their heads, and let's do, I don't know, 7, 6, sure, looks good. let's say we had those values, and again, I'm doing a left Riemann sum. So left Riemann sum means I'm using the leftmost point and going out to the right. Left point, go out to the right. Left point, go out to the right. And what's kind of interesting here too is check out that 18. On the left function, because we did a left Riemann sum, the 18 never got used. That will happen in a right Riemann sum where the left point is not used. So this point that I gave you, 7, 6, I'm not actually using that point. Just like I never had a height of 18 over here. There was no height of 18. So some of the data isn't used. And that should make you feel like, wait, that means we're inaccurate. We should be using all the possible data. And you're right. There are more accurate ways of doing it. And eventually I'll show you trapezoid rule tomorrow. So for here, what could your curve look like? Well, I could have a line. I could have some sort of concavity. It doesn't really matter. No matter how you draw your line over here, some curve that's happening. This is now an over or under approximation.
Over.
This is an over approximation. So I can write this up here, but this is an over approximation.
Does it happen when the like L of t is increasing? It's an under approximation, and when L of t is decreasing, it's an
If
over.
it's a left Riemann sum.
Yeah,
I mean, that's
so-
over this, right? And then I'll switch.
Both of what you just said is 100% accurate, and it's basically my next line. If, and can you, just say it again, Claire. What you said was perfect.
When L of t is increasing, it's an under approximation, and when L of t is decreasing, it's an over approximation.
If it's going up, this is a function that is going from down to up. If it's going up, it doesn't matter what the concavity is. It doesn't matter if I have any curvature to it. If I'm going up, if I'm increasing, then it's always going to be an under approximation. And as Arrow said, this only applies to a left Riemann sum. When I say right Riemann sum, this is going to be flipped. And then an over approximation because we have this thing was decreasing. This function was decreasing. And I haven't memorized these yet. I still need to do my speed sheet, I suppose. I always, every single time on the test, I have to draw it out and then draw one of these graphs. I'm like, is it? Oh, okay. The triangles are above, so I'm not including those. I'm an under approximation. So if you get confused, try to go back to this representation, actually drawing out your data, and then you should be able to get your answer. So let me write down what Claire just said down here. It's
Increasing is under.
so we wrote it's an under approximation, but why? They'll ask you why. If you don't write why, you don't get your point. We'll say because L of t is increasing. Done. Now we have the correct reasoning. All right, let's move on to the second of the three things that we're going over today. Oh my gosh. Wait, I'm like, we get out of here in 5 minutes? No, it's a Thursday schedule. We have until 18, okay. A right Riemann sum. Go ahead and draw the tail correctly. Go. Draw the tail. Does it go right, left? What's going on? Go ahead and analyze the table. You guys are drawing it all. Okay, yes. So you should be drawing things that look like this, where it's a Tetris piece now to the right. Tetris piece now with the tail on the right Riemann sum, tail on the right. And hopefully you have ignored the first point, 0, 18. I'm not using that 18 up at all.
Why are you using that 18?
It's just the way that a right Riemann sum works. So it's an inefficient method, this right Riemann sum, because we can't use that 18 up anyway. A right Riemann sum means that the tail is now on the right side. All right, so I'm going to go ahead and graph all of this data. The right graph, just ignore for now. It's going to be very helpful to see what happens with, if I have an increasing function, I'll make up random points for you. So graph 0, 18, graph 1, 12, graph 3, 8, and 7, 6.
Wait, you use 18?
I just graphed each of these points. I graphed 0, 18, I graphed 1, 12, 3, 8, and 7, 6. All 4 of those points have now been graphed right there. All right, so it's a right Riemann sum, which means I'm using the rightmost point. And another way of thinking about it is on the interval between 0 and 1. On that interval between 0 and 1, I have a height of 12. A height of 12. I'm using the rightmost point, and I'm making a rectangle.
So left
Between.
sums are always
Using a point on the left, exactly. So between 1 and 3, I have a height of 8. Height of 8. There's that rectangle. And then finally between 3 and 7, I have a height of 6. And there's my rectangle. All right, let's go ahead and calculate each of those areas individually. Shout them out. First rectangle,
Whoa.
second rectangle,
60.
third rectangle. 6 times 1, 2, 3, 4.
24.
24. All right. And then how do you show your work? Because they very often on the AP test, they will not give you a graph. They just say, hey, use your table, find it. The way that you show your work is you say, okay, I'm going to do 1 minus 0, 1 minus 0 times the height of 12 plus the next one. 3 minus 1, 3 minus 1, all that times the height of 8 plus the next one. Plus 7 minus 3, 7 minus 3 times the height of 6. And if I do all that math, I'm just going to skip some work now. Let's see. 1 minus 0 is 12. 3 minus 1, 2 times 8 is 16. 7 minus 3 is 4. 4 times 3 is 24. Add them all up and I get 52. Someone correct me?
Yeah, I got 52.
52. Okay, what are our units? Why is it feet, Claire?
Because it's the integral of L of t.
Exactly, yeah. So L of t is still measured in feet per hour. So whenever I take the integral, get rid of one of the times. If it was squared, get rid of the square. If it was just normal hour, get rid of the hour, and I'm just left with feet. Again, if I take the derivative, I'm adding on a time unit. So if I took the derivative, I'd say feet per hour squared. All right, and is this graph right here an over or an under approximation?
It's an over approximation.
So under approximation.
So to figure that out, let's graph it. I always have to come back to graphing it too. So go ahead and just draw any line that you want in between. You can do straight lines. You can have a curvy line. It doesn't matter what shape of line you have here. I'm going to make it look gradual so
Okay, it's an
it
under
looks nice.
approximation.
Yeah, exactly. So when we draw the graph through there, we're missing these areas right here. So again, this is an under approximation. It's the flip of the other one, right?
So if you're decreasing, it's going to be an under approximation.
If it's a right rectangle.
And then if you're increasing, it's going to be an over approximation, I'm guessing now?
Exactly, yeah. Because decreasing. And if you don't like the word decreasing, you can say going down, because it makes more sense that I'm going down for each of these points. Or you just think about your y values or your capital L of t values are going down. So let's come down here and type in our answer. This is the answer that you will type on the AP test as well. It'll say under approx, you can abbreviate too, they'll be okay with that. But I'm gonna say under approximation because capital L of t,
You need a space in between under and approximation.
they're 2 words? Oh, darn it, all right. Because L of t is decreasing. Done. And sometimes what happens is you'll be increasing and decreasing. So if this L of t is decreasing, but if you want to be very specific and cut out a segment of your table, you can say decreasing on the interval from 0 to 7. Because sometimes maybe if I had -1 was actually increasing, and maybe it went from 6 back up to 7, that's increasing too. I need to cut out a segment and say, hey, the segment that I'm talking about is between 0 and 7. So sometimes that does happen too. I'll leave that there. So what happens on the other case? Let me show you the visual representation. Let's make up some points here. Let's go 0 for something that's increasing. Let's do 1, 6. Let's do 3, 10, and I don't know, 7, 16. And what would happen there? Again, I'm using the rightmost point. So this is the rightmost point of the rectangle. And I would be making a rectangle that looks like that. A rightmost point making a rectangle that looks like that. Rightmost point using that point. And here's our rectangle. And sketch whatever sort of function that you want that goes through these points. So I'm just going to do a kind of a straight line because I'm getting lazy. And we can clearly see that now this is an over approximation. Over approximation. And why? It's because we are now increasing. Again, if you ever get confused, at least remember that a right Riemann sum uses the rightmost point for the rectangle, and then just sketch it. You'll be able to tell very clearly from your sketch. All right, and finally, we have the midpoint sum. take a guess. Do you think that midpoint sum is going to be more or less accurate than our right or left Riemann sums?
It's going to be more accurate because it's the average of the two.
And then can it be improved? I guess is the next question on top of that. So yes, midpoint sum should always be more accurate than a left or a right. It is a superior version of our integral, but it's also a little bit harder to find. More complexity, but it also gives us more accuracy, and that's kind of the way it always works in mathematics. So I'm giving you a ton of points now. Let's write them all down. 0, 5, right there. 1, 8, right there. 3, 10, right there. 4, 12, and if you haven't figured it out, I'm just using these table values. 6, 13, 7, 18, and 9, 20. All right, so we have all of our different points. I want to find middle points, and it doesn't make sense to overlap them. I can't use a point here and use a point there and overlap these in any way. So do you guys see what I'm talking about? I can't overlap these integrals between, oh, let me come back, I did that wrong. I can't overlap these integrals like that. I can't overlap like that. So we have to have some systematic way of doing it so that the middle doesn't overlap. The way that we do that is we go every other point. So what I mean is I'm only going to use 0, then 3, then 6, then 9. I'm kind of ignoring the 7, 4, and 1. So what is the middle height between 0 and 3? 8. What is the middle height between 3 and 6?
12.
And then the next one is 18. So it kind of has this cool little zigzag pattern now.
Right.
So our Tetris analogy is now broken down. The next Tetris piece will work, and it is a Tetris piece tomorrow, but this one is not. It's a cool pattern. Maybe I should get rid of all of my crosses so that they look better. Yeah, so you're having this diagonal pattern, which means between 0 and 3, I have a height of 8. So between 0 and 3, I have a height of 8, which is the middle point between 0 and 3. So there's our first rectangle. The next one says between 3 and 6, I have a height of 12. So between 3 and 6, I have this height of the middle point right there of 12. Everything is matching graphically. We're not accidentally stacking our midpoint rectangles. And then I can probably just go without even looking at the table. Well, between these 2 points, I should have that middle point height. And what's happened here? Well, between 6 and 9, I have a height of 18. Yeah, between 6 and 9, I have a height of 18. It matches the table. We're checking our work. And there is our graph of a midpoint sum. Now we have to do some math. So what is the area of our first rectangle? It's 3 times 8, 24. This one is also 3 times 12 now, 36. Now 1, 2, 3 times 18. Yes, it is indeed 54. And again, we have to approximate this. So the way that you show your work is you say, okay, I'm doing 3 minus 0 times 8. 3 minus 0 times the height of 8 plus 6 minus 3 times 12. 6 minus 3, all that times 12 plus our final one, 9 minus 6, 9 minus 6. Quantity times the middle height of 18, and let's add these up. 24 plus 36, that's 60. 60 plus 50 is 110. Add the 414. And our units are what, Gio? If I'm taking the integral of L,
Feet.
it is indeed feet. Cool, so that's all I have for you guys. The one thing I will say before leaving is this. Normally, I would say like 80% of the time I'm pulling a number, making it up. I would roughly guess that 80% of the time they're not going to ask you, is this an over and under approximation? So notice that we didn't do the analysis. That's why I'm not doing it here. But sometimes they do. And you have to use a bit of logic. Like, so if I had my curve here, you'll have to have some sort of concavity maybe, or maybe they'll tell you they're connected by straight lines. What's actually happening? So if I had exactly straight lines, it feels like they kind of balance each other out. Is it an under or an over approximation? Usually they don't ask this question, but this is a horrible question. They wouldn't ask something that this unclear. Usually they'll ask something that's a lot clearer.
Under.
I feel like it's
And I can't even tell. It looks a little bit under to me too. These are just so skinny of a triangle. But you could actually calculate what the area of each of these triangles are to prove it. I'll leave you with that.